Welcome to Lecture 1.3, Linear Maps. We begin with the definition. A linear map is a function, let's call it t, between two vector spaces, v and w. We assume that these are both vector spaces over the same field f. And it has to satisfy the following property. T of ax plus by equals a times tx plus b times ty. And this has to hold for all x and y in V, for all vectors, and for all scalars a and b in F. Now, there's an alternate definition of this. Instead of this one single condition, you could break this into two conditions, and you could say that first of all, t of x plus y equals t of x plus t of y, and secondly, that t of ax equals a t of x, and you should say this holds for all x and y in V and for all x in V and a in F. So some people prefer this single definition because it's just one condition and it's one line, though it's more complicated, and others prefer these two because this says you can break apart sums and this says you can pull out constants. When the vector spaces V and W consist of functions, for example, C infinity, R bracket x, that is the space of polynomials, or the space of 2π periodic functions, we often use the term linear operator in terms of map. I don't know why, that's just historically what's been done. For example, the differential operator, ddx, and the integral, these are linear operators. When our vector space is Rn, we usually just say linear map or linear function. For example, f of x equals 3x and f of x1, x2 equals 8x1 minus 3x2, these are linear functions because they satisfy this condition. Let's check these individually just to make sure we understand why this condition holds. So the first one, f, notice that this is a function from R to R, or R1 to R1. You input a number, you output a number. So here, my vectors and scalars happen to be real numbers. But let's just check that this indeed holds. So f of ax plus by, by definition that is 3 times ax plus by. And now we can write this as 3ax plus 3by. And now we can write this as a times 3x, which is f of x, plus b times 3y, which is f of y. So indeed, this linearity condition holds. Let's check this function now. Now, this is a function. F goes from R2 to R1. So the input is a two-dimensional vector. So this is a little bit beyond the scope of the class. Now, it's not necessarily harder than, you just may not have seen it, and we're not really going to use it much, but I'll show it to you because I think you can handle it. Functions like these from Rn to Rm can be written as matrices. I think I've said that before. So in particular, the input is a vector x1, x2, and then the output, so f of this vector equals 8x1 minus 3x2. It turns out that you can express this function as multiplying matrices. So if I put a 8 here and a negative 3 right here, now this is a 1 by 2 matrix, this is a 2 by 1 matrix, and here f of x1, x2 simply equals, well, let's do this, equals that. So this is a way to write this in matrix form. Now let's check that this is indeed linear. So let's take f of And I'm going to write it now in vertical form. So f of a times x1, x2 plus b times y1, y2. So remember, I can always write an ordered pair vertically if I want to. So for example, this I'm thinking of as f of x1, x2. Okay? So let's compute this is. This is equal to 8, negative 3 times a times x1, x2 plus b times y1, y2. And now matrix multiplication is just like regular multiplication. It's associative. You can pull out scalars. So I can write this, oops, I forgot my equal sign here. I can write this as a times 8, negative 3, x1, x2 plus b times 8, negative 3, y1, y2. And now look what we have here. This is a times f of x1, x2 plus b times f of y1, y2. So I'll write this as a times f of x1, x2 plus b times f of y1, y2. And of course, I think it's easier to write this in this form than it is in this ordered pair form, especially when you're adding vectors, because that would make this a little bit messier. But notice that this indeed checks out, that yes, f of a linear combination, you can break apart the sums and pull out the constants. This is indeed a linear function as well. Next, we need two definitions. First of all, the kernel, or sometimes called the null space of a linear map, we write it as KER of t, is just the set of vectors that get mapped to 0. So formally, kernel of t is the set of all vectors in the domain such that t of v equals 0. The image, or the range of t, is just the set t of v, or the whole space. In other words, we'll write it as im of t, or sometimes t of v. It's the set of all vectors of the form t of v, where v is in the domain space v. Now I want you to remember these definitions because we will use them throughout the class, especially the kernel. Let's do some more examples of linear operators, this time from calculus. So now let's let v and w be the space of smooth real-valued functions, although I might modify this in a later example. First example, let's let t be the differential operator d dx. This is a linear operator from the space of smooth functions to itself. In other words, you input a function f of x and you output its derivative f prime of x. Now I've already said why this is linear, but I'll show it to you again. You take d dx, you take a f plus b times g, first two functions f and g and two scalars a and b. You can write this as a times d dx of f plus b times d dx of g. So nothing tricky about this. Just use the basic definition of linearity. Same thing for the integral. This is a linear operator that inputs a smooth function and then it outputs another function, namely its integral. Now let me say a few things. First of all, you can integrate more things than just are smooth. Like the absolute value function or a piecewise function is not a smooth function. It's not in this space, but you can still evaluate its integral. So really I'm just restricting this linear operator to this vector space. I'm saying forget about everything else. So that's the first thing, and there's nothing wrong with that. Secondly, you have to be careful. Notice that I'm not putting in any limits in here, because if I did, I would have to worry about things like convergence. Like if you integrate the function x, say x from negative infinity to infinity, it's not going to equal anything. So that does not exist. And even if you just have finite limits, you might have to worry about things like 1 over x, some sort of asymptotes. Although technically, this is not a real valued function, 1 over x, because it's not defined on the whole real line. But in general, there are issues you need to worry about, but just defining this as the indefinite integral gets around at least most of those. Finally, the Laplace transform, L, is a linear operator as well. So if you remember from your ODEs course, this is a function that inputs a function of time, f of t, and then you do this weird thing where you multiply it by e to the negative st, you integrate out dt from 0 to infinity, and what you get is actually a function of s. So sometimes we write this as capital F of s. So this is a linear operator that inputs little ft and outputs big F of s. And this is linear for the same reason why integrals are linear. So let's do both of these. So an integral of af plus g, I guess bg dx is a times integral f dx plus b times integral g dx. So that's why this is linear. And why is the Laplace transform linear? Well, the Laplace transform is just an integral. So let's check for practice. The Laplace transform of af plus bg. So this is a function of t. I'm not going to write that. I don't really need to. This is the integral from 0 to infinity of af plus bg times e to the minus st dt. And of course I can break this apart as the integral of a times 0 to infinity of f. I'll write f of t e to the minus st dt plus b times the integral from 0 to infinity of g of t e to the minus st dt. And this is simply a, now look at this creature, that is just Laplace transform of f. Now this of course is a function of s, I don't need to write that. And now we have plus b times this creature, which is Laplace transform of g. So notice this is linear because Laplace transform of af plus bg is a times lf plus b times lg. And there are a few other little technical issues you need to worry about with this. Technically, you can't take the Laplace transform of any smooth function because this integral may not exist. So generally, these are defined for all functions that are, I think we say, that don't grow faster than an exponential function. And I think I'll just leave it as that, at that. So technically, I can't say that this is a linear operator on this space. I have to look at a smaller vector space, namely those functions that grow no faster than exponential functions. And in that case, this will be a linear operator. Let's return to our example of thinking about matrices as linear maps. And we'll do a 2x2 example because that's the simplest. So consider a 2x2 matrix A. So here's one, A11, A12, A21, and A22. Now you can multiply a matrix like this by a vector, x1, x2, and if you do that, you get another vector, y1, y2. So you can think of this matrix as a black box where you input a vector, x, and you output a vector, y. Now here's a formula for what that vector, y, is. And you all know how to do this. Remember, to multiply matrices, you multiply rows by columns. So this first entry, y1, is what you get when you multiply this row times this column. So that's a11, x1 plus a12, x2. And this second entry, y2, is what you get when you multiply this row times that vector, that column. So a21, x1 plus a22, x2. Let's revisit some basic facts about matrices. and try to understand them in this new light of thinking of a matrix as a linear map. So most of these I'll assume that you've seen before, although if you haven't, that's fine. And it's really not a big deal because this is not going to be the focus of the class. But I think it's worth showing it to you because, again, you've likely already seen them, and seeing them in this new light is only going to help solidify your understanding. So the first thing is that the determinant of a matrix is the scaling factor of this linear map. I'll explain more shortly. Now you know from vector calculus that the determinant of a matrix is the area of a particular parallelogram. I'll say more about this shortly. And the determinant, I had to put absolute value signs around it because though area can't be negative, the determinant can. And the determinant is negative if there was a reflection involved. The second fact is that A is invertible if and only if the determinant is non-zero. So let's do some example, or let's do a picture of this to help solidify both of these concepts. So I'm going to start with R2 right here, and I'm going to take our standard basis, E1 and E2, and that determines a grid. So you think of R2 as this grid, and now if you apply the matrix A, what does that look like? Well, let's see where E1 gets mapped to. Let's suppose that E1 gets mapped up here. So this is A, E1, and let's suppose that E2 gets mapped over here. So this is A, E2. Now this determines a grid as well. So let me try to draw this grid. I don't know how well I will do. I'll try. So this is going to be a grid of parallelograms. So here's how I want you to picture this. Picture coming over to this side and taking E1 and E2 and picking them up and dragging them. So take E1 up to here and E2 up to here, I guess down here, and drag them there, and suppose that the grid goes along for the ride. You know what I mean by that? So that wherever you pull these vectors, the grid goes along with it. So you get this grid of parallelograms. Now several things. So you can determine the image of every vector just based off of this grid. So for example, this vector right here, say let's call this V, this is say 2E1 plus E2, where does that get sent? I'll come over here and go to two steps in the E1 direction and one step in the E2 direction, and you get up here. So this is A times V. And you can do this for any vector. So this, let's do another one. So let's see up here. So this guy is called this W. This is E1 plus 3 E2, and that gets sent to E1, AE1 plus 3 E2. That gets sent here. So this is A times W. And again, you don't need to do this just at the lattice points. You can do it anywhere in the middle as well. So the area of the unit square over here is clearly equal to 1. So area equals 1. And the area of this parallelogram is the determinant of the matrix A. So that's what I mean by the determinant is the scaling factor. So this grid gets blown up by whatever this area is. Now this particular determinant is negative because notice that E1 and E2 swapped locations. So informally, if I start at E1, I have to go counterclockwise to E2, but over here I have to go clockwise. So that happened because there was some stretching involved, but also because there was a reflection. So this thing got reflected, so the determinant is negative. Now, this next fact, I said A is invertible if and only if the determinant is non-zero. So why is that true? Well, first of all, what does it mean to be invertible? Well, that means that there is a backwards map, say A inverse, such that if you do if you start here and then you do A and you do A inverse, you get the identity. So that means that if you do A and then A inverse, you get the identity. Now we usually read these things right to left because of this multiplication notation. But you can also start here, the right-hand side and then do A inverse and then A, and you need to get the identity as well. So this is what it means for A to be invertible, is that there's some matrix A inverse, so that you multiply A inverse by A on either side, you get the identity. And the identity is just the do-nothing map. So it means if you start here and you do A and A inverse, you get back to where you started. Now, when is this possible? When is there such a map? Well, notice that anytime these vectors, AE1 and AE2, are not collinear, meaning they're not in the same line, then we can just move them back to where they came. So we can define the inverse map that sends this AE1 down here, over there, and sends AE2 up to the y-axis. And that just undoes what the map A did. And this is possible if and only if these things are not collinear. And that is true if and only if this parallelogram has a non-zero area. So notice that the other case would be, let's suppose you had another map, let's call it B, and suppose that for this map, so we're reusing this picture for the domain, suppose that B times E1 was here and B times E2 was here. It was a scalar multiple of that. Then this whole grid would get collapsed down to a single line, and the area of this parallelogram, well, it's now just one-dimensional, so the area is 0. In this case, you can't pull apart these vectors. There's no way that you can invert this map because you've already collapsed a dimension. So that's the geometric reason for why this basic algebraic fact is true. Next, it's easy to see how this construction of thinking of 2x2 matrices as linear maps from R2 to R2 generalizes to higher dimensions. So an m by n matrix represents a linear map from Rn to Rm. So I'll do an example below, but I'm not going to draw it because, well, you just can't visualize or draw higher dimensions. So first of all, it's easy to get confused as to which is m and which is n. So hopefully I will show you a reason, and so you'll never get confused again. So let's consider an m by n matrix. So here's how I always think of it. I draw an L like this. So I go down and then over. And I say if this is m by n, then that is m by n. So m by n means m, what is this, rows, and this is n columns. So that means that these entries are A11, A12, and A1n, A21, A22, A2n, and this goes down to AM1, and then up to AMN. The second trick is notice that these subscripts, if you read them as you would a book, from left to right, column or row by row, they are in increasing order. Now we say A11, A12, but think of these as 11, 12, 13, and so forth, and then 21, 22, 23, etc. So if you do this, you'll never get m by n confused again. So this represents a linear map from Rn to Rm. That means that we can multiply this by an n-dimensional vector. So this as a matrix is n times 1. N times 1. So let's write this as x1, x2 to xn. And if we do that, well, what do we get? We get an m-dimensional vector. So as a matrix, this vector is an m by 1 matrix. So m by 1. And again, I'm drawing that L. M by 1. N by 1. And so you know how to multiply these matrices. So it's this row times this column. I'm just going to call this y1 and y2 all the way up to ym. Now, I guess I'll do the first example. So this y1 is really, again, this row times column, which means it is a11 x1 plus dot 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 up to a1n xn, and then so forth. I'll do the last one, a m1 x1 plus to a mn xn. So one last little piece of advice, notice that you can only multiply two matrices together if these inner numbers are equal. So here m by n times n by 1, and the result ends up being, well, look at these two outer numbers, m by 1, m by 1. So just another trick as well. So again, I can't really visualize this because we can't view n or m-dimensional space, but algebraically, this linear map can be thought of as a black box that inputs this n-dimensional vector and outputs an m-dimensional vector. Now, unless m or n and m are equal, you can't speak of things like determinants or invertibility, things like that. So this matrix is a map between two different vector spaces, Rn and Rm. And for a map to be invertible, it has to be between a vector space and itself. I guess other maps can be, well, yes, I'll stick with that. For a matrix to be invertible, it has to be from a vector space Rn or R2 to itself, and the determinant only exists for a square matrix. Here's the last fact I'll show you, and this actually holds more generally, not just for maps of matrices from Rn to Rm, but for maps between any vector spaces. So let's suppose A now is a linear map from a vector space V to a vector space W. So this says that the image of A and the kernel of A are both subspaces. Now let's pause for a moment and let's think about where these things live. So the image of A that's the range, that lies in here. So this is a subspace of W, whereas the kernel of A, this is everything in V that gets mapped to the zero vector. So that lies in V. So even though these things are subspaces of different vector spaces, they satisfy the following remarkable relation, that if you add up the dimensions of these guys, the dimension of the image plus the dimension of the kernel, you get n. And n here is this is the dimension of the domain space V. So here that was given, but just in general, let's say this is n-dimensional and this is m-dimensional. Now, intuitively, what this says, this is often called the Rank-nullity theorem, is that every dimension in the domain either gets collapsed to zero and is part of the kernel, or it persists and it's part of the image. So let me see if I can draw a picture of this. So here's R3, and let's take a linear map from R3 to R3. This is A, and let's suppose that, well, here's E1, E2, and E3. Let's make this easy. Let's suppose that these three vectors get mapped to AE1, AE2, and AE3. Let's say that these things get mapped to a plane. So here the image of A is, so let's look at this equation. So the image of A, in this case, is two-dimensional. What's the kernel of A? Well, we don't really know what the kernel of A is, but what's n? N is 3. The domain is three-dimensional, so let's put a 3 here, and now we know right away that the kernel of A is a one-dimensional subspace. So it's some line, so somewhere over here there is some line, I don't know what it is, that gets collapsed entirely to 0. So this is the kernel of A, and every vector in here gets mapped to 0 via this map A. So this is a beautiful theorem. Again, it's called the Rank-nullity theorem. It will come up in any basic linear algebra course that you will take. I said in the very first lecture that Linear algebra underlies nearly every aspect of the mathematics in this course. And the better you understand linear algebra, the better you'll understand the big picture in this course, which will just make things easier. Now, it shouldn't really be clear at this point why or how that's true, because this is a course on differential and partial differential equations, and things like modeling heat flow and waves, and things like Fourier series. So where's the linear algebra? Well, at this point I want to give you a little bit of a preview, and we'll do a lot more of this later. So let's let V and W be the space of smooth real-valued functions, and let T be the following differential operator, d squared over dx squared. So this is a linear operator that inputs a function, y of x, and spits out its second derivative, y prime. First question I want to ask you is, what is the kernel of this operator? Well, the kernel of t is, by definition, the set of all real-valued functions, y of x, whose second derivative is equal to 0. Now, what functions have their second derivative equal to 0? Functions that look like this, c1x plus c2. So these are polynomials of degree at most 1. So c1 and c2 can be any real number. Okay, maybe you don't see the connection just yet. So let's do another example. Here's another differential operator. So this one, big T, is d squared over dt squared plus k squared. So let me pause a moment. What does it mean when I say this is a differential operator? Well, let's look at this. Let's go up here and say, well, if you take d squared over dt squared and you apply, plus k squared, and you apply it to a function y, well, then you can just think of this as just so-called multiplying this by k squared and by this. You just append it and you get the second derivative of y plus k squared times y. So d squared y over dt squared plus k squared y. So this is indeed a legit differential operator. And I claim it's linear. Let's see why it's linear. What does it mean to be linear? So it's linear if t times a y1 plus b y2 is, down in the lower right, I'm going to say a times t y1 plus b times t y2. So why does that happen? Let's check. So what is t times this? So that is d squared over dt squared plus k squared applied to a y1 plus b y2. And we can multiply this out just like we would a polynomial. So it's these two terms. So this is a times d squared y1 over dt squared plus these next two terms. So plus b times d y2 squared over dt squared plus k squared times each of these. So plus k squared a y1 plus k squared b y2. Now if we regroup these things, we can write this as, as a times d squared y1 over dt squared plus k squared y1 plus b times, so there's this term and that term, so b times dy squared, y2 squared over dt squared plus k squared y2 squared. Oh, I forgot my 2 over here. And notice that this is indeed a times t of y1 plus b times t of y2, and so yes, this checks out. This is indeed linear. Okay, so it's linear. It inputs a function y and spits out that function's second derivative plus k squared times the function itself. And what's the kernel? The kernel of this map is all of these y of t's that get mapped to 0. Now what does it mean to get mapped to 0? That means that this guy is equal to 0. Y double prime plus k squared y equals 0. Now look at this. What is that? This is a second order differential equation. A second order linear differential equation. And in fact, that is why way back when you probably learned what it means for an ODE to be linear without any justification as to what that means. And basically that just means that it arises from a linear operator like this. Okay, so do you remember what the solutions to this differential equation are? Well, you should, but I wouldn't be surprised if you don't, because for whatever reason, it's something that once students learn and they take a few months off, they likely forget it. So you look at this, you should think sines and cosines. So the solution is C1 cosine of kt plus C2 sine of kt, where C1 and C2 are real valued functions. So notice, this is a differential operator of order 2. You get a differential equation, and what you get here is a two-dimensional vector space. This is not a coincidence. Now, just as a reminder, if this plus sign had been a negative sign, if this had been y double prime minus k squared y equals 0, now that's going to come from the differential operator where this plus is a minus. But do you remember what the solution to this is? That is c1 e to the kt plus c2 e to the minus kt. So more on this later. One more example. Consider the differential operator, same one as above, but this k squared is now a t squared. So you should look at t and think, well, this is not a linear function. But this is still a linear operator, because you can do the same thing that we just did to check that t times a y1 plus b y2, which is d squared over dt squared plus t squared times a y1 plus b y2. And if you multiply this out, it doesn't really matter if this is a k squared or a t squared. What you're still going to get is that this is equal to a times t y1 plus b times t y2. So yes, this creature is a linear operator that inputs a function y and outputs its second derivative plus t squared times the function itself. And the kernel of this linear operator is the set of all functions, y of t, that solve this differential equation. So you probably wondered way back when you learned that this was a linear differential equation, well, how could that be? Because t squared is not a linear function in t. And your teacher or your book might have said, well, that's just the rules. Well, this is why it's the rule. Because linear differential solutions to linear differential equations arise as kernels of linear operators. Now there's a few technical details that we need to work out in terms of what it means to be homogeneous versus just linear. We will do that in later lectures. But also one more detail is that I want to emphasize is that this is a second order differential equation, and I'm not going to solve this. You have to separate variables, and it's not something you can probably do in your head, but the solution to all of these second order differential equations are going to be two-dimensional vector spaces. So the solution to this is going to be of the form c1 y1 of t plus c2 y2 of t for some functions c1 and c2. That solves this. And actually I lied when I said you have to separate variables. It's a little more complicated than that. That's what you do for first order equations. For second order ones, yeah, this is more complicated. I think you have to do a power series trick. But that's something you'll learn about later. Let me summarize what we just learned. And remember, this is still a preview. We will go into it in more details in the next set of lectures. So the big idea in the last slide was that the kernel, or the null space, of these linear differential operators are solutions to corresponding linear differential equations. And they turn out to be homogeneous because the right-hand side was always equal to 0. So we had something like y double prime plus t squared y equals 0. The fact that this thing was 0 means that the equation was homogeneous. And that's probably something that might ring a bell for you a long time ago. And don't worry about it if you don't remember. We will go over this later in this class, and not that long from now. But right now, the takeaway message is that the kernel of these linear differential operators are solutions to linear differential equations. Moreover, since the kernel of an operator is a vector space, then the set of solutions to these differential equations, which we often call the so-called general solution, well, the general solution is a vector space. And that's how vector spaces arise in differential equations. And we'll see a lot more of this fairly soon. So stay with us.